First, let us consider the significance of the energy levels. We now have a very precise result for a physical system, so here's a corresponding diagram. As I emphasized, what we have determined so far are the bound states of the system, which all have a negative energy. The lowest state is the ground state, and it has an energy of -1 Rydberg. Above this we have the excited states, which accumulate close to zero when the principal quantum number increases. The reason for this is of course the shape of the Coulomb potential sketched here. This lets electrons escape at positive energies, and you indeed find extended states at these energies. Now, if we could find a way for this system to change its energy, and we will do so in the next chapter, then we could imagine it to relax into the ground state as a sort of energetically beneficial state, say by releasing the energy by emitting a photon. And if we add sufficient energy, the electron can reach an extended state where it can then fly away. So this would describe ionization, and from the ground state the threshold for ionization would just be the Rydberg energy. Let us compare this to the energy levels in the other two problems that we could solve exactly. That's the harmonic oscillator and the particle in the box, for which I here show the levels in the one-dimensional case. As you can see, the particle becomes more and more confined by the potential when we pass from one system to the next. And this has the effect to spread the energy levels out as their energy increases. So it affects the density of states. In addition, the density of states increases when we increase the dimensionality of the system. Recall that on top of the accumulation close to zero, the energy levels in the hydrogen atom also become increasingly more degenerate. In practice, this means that it can become quite difficult to distinguish the highly excited states, especially if you then also account for the center of mass motion that adds some further energy, the finite lifetimes in these states, and other physical perturbations of this idealized picture, such as the presence of other atoms nearby. Nonetheless, atoms in highly excited states are a very active research subject. They are called Rydberg atoms, and interestingly, they are quite stable. Speaking of ways the system can change its energy, this can also occur between different bound states. These transitions can be organized into so-called series, as shown here. They have been observed already long ago. These are the names given to the spectral lines that people observed well before quantum mechanics had been conceived in the emission and absorption of light by such atoms. Spectroscopy rapidly evolved into a precise tool to study atomic systems, and this continues with modern advances. As we will see later, these transitions follow some interesting rules, so-called selection rules, which are related to conservation laws. Already quite early in this development, researchers managed to resolve a very detailed additional structure, which points to subtle effects that we have neglected so far, for instance involving the electronic spin. We will come back to this very soon, but first look in some more detail at the atomic orbitals. These atomic orbitals carry some bespoke names as indicated here. First of all, we substitute the angular momentum values L by some letters of historic origin. They were coined for the spectroscopy of alkali metals, where they signify sharp, principal, diffuse, and fundamental, so L equal to 3 would be F. So you can anticipate that these orbitals are not only relevant for hydrogen. After all, the angular dependence is the generic part of the solution in a central potential, at least for just one particle. And so we will return to this later when we discuss quantum systems with more particles. And we precede these letters by the principal quantum number n. As n needs to be larger than L, we get the indicated combinations. Next, we can visualize these orbitals by prescribing a surface of a constant probability density that includes, say, 95% of the probability. I show such surfaces here. The s orbitals are all rotationally symmetric, but the p and d orbitals have different shapes, and I show a representative one for each case here. In the ground state we only have the one s orbital, and when we write it down we see that this simply decays exponentially with the radial distance. This then translates into a corresponding decay of the probability density. What I write down here is the radial probability density, which has an extra factor of 4 pi r squared, because here we just ask about the likely distance of the electron to the proton, irrespective of the direction. And now, as indicated in the sketch, this has a maximum when r equals the Bohr radius. In the first excited energy level, we find the 2s and the 2p orbitals. The 2s orbital has now an extra factor just depending on the radial distance, which actually vanishes at twice the Bohr radius. So here we find a nodal surface, which is the extension of the nodal points we discussed for the excited states of one-dimensional systems. In our visualization of these orbitals, this nodal surface lies between the two interior spherical surfaces. There are 3 2p orbitals corresponding to the values of m equal to -1, 0 and +1, given that L here is equal to 1. For m equal to 0, we find that the exponential is multiplied by what is really the z-coordinate in Cartesian coordinates. So there is then a nodal surface where z vanishes, hence in the xy plane, and the orbital looks elongated into the z direction. We call this the pz orbital. In the other 2p orbitals, the factor in front turns out to be x plus or minus iy. Now, as these are degenerate in energy, we can recombine them into 2 new orthogonal orbitals, where we just have x and y there. These are then just our rotated spherical harmonics, so eigenstates of Lx and Ly, and we call these orbitals px and py. You can carry on. With n equal to 3 you get additional nodal surfaces and the more complicated d orbitals, and this continues as you further increase n. To complete this discussion, let me mention what we have neglected, rectify a major part of this, and use the remainder for an outlook. The main piece that is missing is the spin of the electron. You can add this in just like we added in the proton position at the very beginning of this segment, so by making the wave function also dependent on this degree of freedom. Conceptually, you can do this in 2 ways, but they're exactly equivalent. Either you say that there are 2 wave functions depending on whether the spin is up or down, or you say that you have a spin but its state depends on the position in space. Mathematically, these are both the same thing. What this then tells you is the probability density to find the electron somewhere in space, while its spin is up or down. This of course implies that spin and position are simultaneous observables. Now, when we assume that the energy of the electron in the hydrogen atom is independent of its spin, we simply get 2 copies of each solution, as well as their superpositions, which would simply give us a spin that is not aligned with the z-axis. Next, we can make this internal structure visible by applying a magnetic field. Recall that we mentioned that a weak magnetic field simply couples to the magnetic moment generated by the orbital angular momentum and the spin, which is how spin can be detected in the Stern-Gerlach experiment, including this extra factor of basically 2. Now, if we again simply align our z-coordinate with the magnetic field, our solutions are still the same as before. They are also an eigenstate of this extra term in the Hamiltonian. However, the energy now depends both on the magnetic quantum number m as well as on the orientation of the spin. So this lifts the degeneracy of these states as indicated here. In spectroscopy, the easily detectable transitions between the energy levels actually occur with a fixed spin, and furthermore only change the magnetic quantum number m by at most 1. This is part of the selection rules that we will discuss in the next chapter, and really arises from the conservation of angular momentum, including the photon that is released or absorbed. So spectroscopically, you then observe that the magnetic field splits any line into 3. This is known as the Zeeman Effect. This really completes our discussion of the hydrogen atom in this course. To give you an outlook on what else there is to it when you further venture down the road into atomic physics, here is a list of effects that you would then include. This just collects and expands on some of the incidental remarks that I made throughout this chapter. Firstly, we included the magnetic field in a perturbative manner. When we do this more systematically, we find that there is also a quadratic term which describes its effect on the orbital motion itself. I already mentioned that this will be covered in a bonus chapter at the end of this course, because this deserves its own attention and can be nicely illustrated in another setting, the quantum Hall effect. For weak magnetic fields, this term can be safely neglected. Next, we only focus on the Coulomb interaction, but the two magnetic moments of the spin and the orbital motion also interact. That's called spin-orbit coupling and leads to the so-called fine structure of the spectral lines. This is a central topic in any course on atomic and molecular physics. It also occurs for electrons in condensed matter systems and is important for the topological states that you can then find there. That's a very active field of present research. Furthermore, the proton also has a spin and a corresponding magnetic moment, but the latter is much smaller. Recall that the Bohr magneton is inversely proportional to the mass of the particle. In atomic physics, this leads to the so-called hyperfine structure of the spectral lines, and it is also exploited in nuclear magnetic resonance, which is a major tool for the characterization of materials, as well as for medical imaging. And I also mentioned that the factor of 2 in the magnetic moment of the spin from the electron has a deeper relativistic origin, and that you obtain a further small correction if you also quantize the electromagnetic field, as you do in quantum electrodynamics. This gives you links to topics that you can study beyond this course. Finally, let me mention the two major open questions that we will indeed address here in the remainder of this course. In the present chapter, we mention transitions, as well as that the atomic orbitals are also useful for other atomic species. Well, in this course, we really have two big topics still to cover: dynamics and quantum systems that are composed out of many particles. And in these discussions, we will also return to these two specific points mentioned here. So let us move on to one of these chapters where we discuss the dynamics of quantum systems.